Hi, I'm Mark Askelson, Associate Vice President for Research with a focus on national security from the University of North Dakota. IEEE-USA iWork Summit is where aerospace, space, and defense collide with cutting-edge tech. If you are a leader in industry, academia, or government, this summit is for you. You'll hear from DoD, Northrop Grumman, and AFRL Regional Network Midwest, and connect with the people shaping what's next. And I will see you on September 10th at UND.
Good afternoon, everyone, and welcome to today's IEEE-USA webinar, Next Generation Microelectronics Manufacturing, Stacking the Future with Mixed Materials 3D-HI. I'm your host, Jonathan Cho. Today's webinar is in partnership with the Defense Advanced Research Projects Agency, or DARPA. Our presenter for today is Mr. Michael Holmes. Mike is the Managing Director of the Next Generation Microelectronics Manufacturing, or NGMM program. Prior to joining DARPA in September 2024, Michael was at Sandia National Laboratories for more than 21 years. In his most recent role at Sandia, he was the Senior Manager of the Protective Technologies Organization, focused on specialized hardware systems securities research. Previously, Mike was responsible for operation of the largest U.S. government microfabrication facilities for the National Nuclear Security Administration's Microsystems Engineering, Science, and Applications, or MESA Center. He held additional roles at MESA, including Senior Manager for the Heterogeneous Integration and RF Microsystems Group, Line Manager for the Application-Specific Integrated Circuits Department, and Mixed Signal Integrated Circuit Design Engineer. Before turning over to Mike, we're going to play a short teaser video about what he's going to be talking about today.
From the palm of your hand to the frontiers of defense, microelectronics power our world. But the industry is at a critical inflection point. For decades, innovation has focused on squeezing more transistors onto silicon chips, but the demands of emerging technologies are pushing this approach to its breaking point. Fabrication costs are skyrocketing, and we're hitting the physical limits of miniaturization. The future lies in a new dimension, 3D heterogeneous integration, or 3D-HI. 3D-HI will revolutionize microelectronics by vertically stacking and interconnecting diverse components and materials, creating high-performance systems that surpass traditional 2D technology. This innovation allows us to move beyond the limitations of silicon, integrating new materials to achieve capabilities essential for both Department of Defense and commercial applications. To spearhead this revolution, DARPA created the Next Generation Microelectronics Manufacturing Program, NGMM. DARPA is partnering with the University of Texas at Austin and its Texas Institute for Electronics Research Center to establish the TIE NGMM Center in Austin, Texas. This open-access 3D-HI manufacturing center will foster a vibrant ecosystem of innovators, from industry giants to agile startups, all working together to push the boundaries of microelectronics manufacturing. This ecosystem will drive disruptive innovation and ensure access to cutting-edge technology for national security and economic competitiveness. 3D-HI will be the engine of tomorrow's breakthroughs, driving innovation across industries and ensuring U.S. leadership on the global technology stage. Join us in building the future with NGMM.
Without further ado, I'll now pass it off to our guest. Welcome, Mike. We're very excited to hear what you have in store for our audience today.
Hi, all. Thank you, Jonathan. Really appreciate it. First, thank you to IEEE for hosting the webinar and giving me a chance to come and share with you the exciting work that we're doing for the Next Generation Microelectronics Manufacturing Program. I'm not sure how I got lucky enough to find myself in this spot helping to support this program, and I'm now just about a year into DARPA, and it's just been an incredible experience to see if we can help move this Next Generation Microelectronics program forward. Huge thanks to the amazing team at DARPA for pulling together that video, kind of summarizing where we are and where we're headed with this program. So again, really look forward to sharing a little bit with you about where we're headed with NGMM, and then have some time at the end to take some questions from you. So next slide, please. So first, for those that might not be as familiar with DARPA and what we do, we really are focused on making these pivotal early investments that can change what's possible. Since DARPA was founded in 1958, we've really been focused on developing enabling technologies that really then create unique and differentiating capabilities for our warfighters. And so if you look at some of the critical enabling technologies, you see investments in really material science, again, starting since DARPA's inception in the late 50s, and sustained investment out through today. And you see critical investments in things like ARPANET, microelectronics, autonomy, and other critical technologies that then enable important military capabilities for our warfighter, like communications and networking, stealth technologies, precision-guided munitions, precision and navigation, and then things like the long-range anti-ship missile. Next slide, please. Again, DARPA's role in this community, in this ecosystem, is really to push for creating breakthrough and paradigm-shifting solutions and pushing specific technology areas to really disrupt or massively accelerate technology roadmaps and drive innovation. You see some examples of that here in the chart with the interface message processor on the left, which was really the very first router that was created, which led to now the modern internet as we have it. Stealth technologies, autonomy through the autonomous vehicle challenge, advanced prosthetics, drone, and then ultimately the long-range anti-ship missile. Next slide, please. Again, one last slide to orient you a little bit to DARPA. I actually sit in the Microsystems Technology Office, or MTO, that's there. But there are 6 total offices, technology offices at DARPA, starting on the left side with the Biological Technologies Office, or BTO. BTO is really focused on warfighter health and diagnostics and technologies in that area. The Defense Sciences Office, or DSO, is really the organization with really a broad science focus. They're doing research on things like turbulence and very, very challenging research problems. IIO, the Information Innovation Office, is kind of the AI and cyber portion of DARPA. MTO, again, the organization that I sit in and the home for the next generation microelectronics manufacturing program, really focuses on microelectronics and microsystems. And we sometimes think of the work that we do in MTO as a tide that helps to raise all ships, given the impact that microelectronics can have on both military and commercial systems. STO, or the Strategic Technologies Office, really focuses on the physical domain and finding, detecting, and tracking. And then lastly, TTO, or the Tactical Technology Office, is focused on design, development, and manufacture of warfighter capabilities and really improving those on all fronts. And there's been some really interesting publications recently associated with work that happens in TTO, including the most recent notification about the Alias autonomous helicopter work that's been done, and a recent partnership with the state of Texas to use those autonomous helicopters to support firefighting in that state. So TTO works with really exciting systems level activities. But today, I'm going to deep dive NGMM and tell you what we're up to for helping to drive the future of 3D HI and advanced microelectronics. Next slide, please. So here's a look, a slide that I've presented several times, really capturing effectively Moore's Law and the development of the modern integrated circuit as we know it today, starting all the way back in the 60s with the development of the planar integrated circuit, and then really tremendous innovation that has continued to increase the compute capability of silicon microelectronics. The ability to integrate faster and lower power and more dense devices into these monolithic chips that then drive the advanced compute capability that we have now, and that's really prolific in our everyday lives and all of the devices that we use. And so we see development of very large scale integration and copper interconnects, and then tremendous innovation in the last decade in new and novel transistors and architectures to support and continue to drive Moore's Law. But Moore's Law is certainly facing both technical challenges, as it really always has. It continues to face significant technical challenges to continue to push that innovation, and also economic challenges. And so we at DARPA really believe that the next wave of innovation, the next generation of advanced microsystems, is going to come by way of 3D heterogeneous integration, and that is the focus of our NGMM program. So if you jump to the next slide, and actually one more. It's worth pausing here for just a minute to talk about levels of integration and kind of what we mean by levels of integration, and in particular, clarifying for DARPA where NGMM fits in this spectrum. Right now, when people talk about heterogeneous integration or 3D heterogeneous integration, it's very, very broad scope, and people use those terms to refer to different packaging technologies, different intimate integration of different devices in 2.5D and 3D stacks. And so I like to start here where, again, tying back to the prior chart and Moore's Law and the innovation that's happened in that space, we can continue to see tremendous innovation in the development of advanced monolithic devices that have more and more compute power and are higher and higher performance to address our modern day challenges in compute and AI and other areas. There now is a focus on the development, one column over here, of 2.5D technology, particularly with silicon, where we're seeing large commercial vendors and commercial foundries support the development of standards around 2.5D silicon integration, and really this chiplet ecosystem that we've been talking about for some time, and this idea of starting to partition and integrate large numbers of silicon chips on a large substrate material, whether that's silicon or glass or organic or some other material. But the integration of many, many silicon chips onto interposer technology or platform, once again, continuing to increase the compute power per unit area and pushing for performance improvement through additional compute, while really pushing forward with meeting the demands of high-speed interconnect and thermal and other challenges as we push towards this 2.5D integration. Still, one column over, there are organizations and folks that are focused really on 3D integration of silicon, and tremendous performance benefits in 3D stacking of silicon, and the opportunity to really tailor each layer in the individual stack to a specific technology node, a specific foundry, and trying to optimize each layer for compute or memory or analog or whatever the specific application is, and the performance benefits that you can get by stacking those technologies vertically. NGMM, for NGMM, we're really over on the far right-hand side here in the last column, where we are really focused on the tremendous benefit of integrating mixed materials, compound semiconductors with silicon into these integrated stacks, where those compound semiconductors can really supplement or complement the performance of silicon to drive advanced compute, to drive the ability to develop sensors and cameras and radars and things that can operate beyond the range of silicon across the electromagnetic spectrum. And we believe that there has been and will continue to be significant impact in the DoD and the intelligence community for these applications, but also recognize a significant commercial opportunity in this space as well. If you jump to the next slide, please. DARPA and MTO have really been making investments for over 25 years in this technology. You can see a timeline up above for significant program investments that DARPA has made to develop 3D-HI and the technologies that support 3D-HI. I suspect there could be a couple of folks that are on the webinar today who have been directly involved in these programs and supported them either as a performer or maybe at DARPA in leading and driving the future through 3D-HI. Most of these programs were focused on either process development, where we were looking at developing new materials to allow us to approach new application spaces or take on new missions. Focus on integration technologies, the way that we bond and integrate and interconnect these devices. Really a core focus area around thermal management. The thermal challenges can certainly be quite significant in the stacking and integration of these devices. And then really pushing for high-speed interconnect or high-performance interconnect through 3D stacking to enable these advanced systems. There's also been some product development focus, looking at specific applications for arrays and sensors, some focus on focal plane arrays and imaging, pushing for advanced devices or high-performance devices in these new materials that can support new applications. And then some effort focused on standards as well for the integration of these systems. So NGMM is really intended to be the capstone of what has been a quite significant investment over more than 25 years in these enabling technologies that support 3D-HI. Next chart, please. So why mixed materials 3D-HI? What are the benefits of integrating these compound semiconductors or mixed materials into these stacks. I have 4 sort of cartoonish diagrams here on the chart that provide some perspective for those who may not be as familiar. I suspect many folks on the line are very, very familiar with the technology and the capability that it brings to bear in specific application spaces. But starting upper left, you see a kind of a cartoon rendering of an advanced radar phased array system, where you've got a control circuit and then some radio frequency circuitry, RF circuitry, as well as an antenna layer that are in this 3D stack. And by tailoring and tuning the RF circuitry and the antenna layer, for that matter, in specific materials, really you can make significant improvements on the performance of that radar for specific applications. Similar for focal plane arrays for imaging, by selecting the particular material that you're using as kind of the transducer or the sensor that's on top of the stack. You can optimize focal planes to target specific application spaces or for specific areas of the spectrum that you're interested in imaging in. And then a couple of additional examples on the bottom for high efficiency power converters and the selection of particular technologies for the power switch for high efficiency converters. And then also communications in the lower right, where certainly tailoring the materials and the technologies you integrate in the stack can allow you to communicate in different spectra for different communication structures and architectures. Next slide, please. A quick look at kind of the impact of 3D-HI and some of the performance benefits that you can see here. Really, this is a look just at a high level of some specific applications and the kinds of performance improvements that you can see across those applications, all the way from maybe a 10x performance improvement up through 100x performance improvements, enabled by not only the intimate integration in a 3D stack, but also specific application and specific technology nodes in that stack and specific materials to enable that performance. And then certainly significant advantage in reducing the size, weight, and power with 10x reductions in volume as you gain the performance improvements as well with these integration of these advanced materials in these stacks. We're really focused on helping to enable faster prototyping timelines as well. And I'll talk a little bit more about this as I get into the how and the what we're doing with NGMM. But we're really focused on some centralized manufacturing instead of multiple vendors that are distributed across the country for enabling this 3D-HI technology, and also really some common approaches or common standards to support production and prototyping of 3D-HI systems. You jump to the next slide, please. Bear with me. This is a little bit cartoonish, so I apologize for that. I suspect some of the audience are very, very familiar with this capability and with some of the challenges here. But I like to use this slide to try to summarize what I think are 2 really key innovation areas for our NGMM program. And if I like to acknowledge the tremendous creativity that the materials community has with developing and maturing new materials, new advanced materials built with the breadth of the periodic table that can help address these challenges and allow us to reach into new application spaces to benefit commercial applications as well as military and national security applications. And so that creativity leads to this very, very broad set of materials that can be sourced from an extensive supply chain, a very broad supply chain, which then results in this set of subcomponents, that are optimized components developed with these advanced materials that are very, very diverse. You can have different wafer sizes all the way from maybe 75 millimeter to 300 millimeter wafers. Those wafers can be different material sets, so they have different mechanical properties, different thermal properties, they're different thicknesses. And in addition to wafers, we can also get subcomponents or modules or pieces of wafers that would be utilized to support low-cost prototyping. So really the diversity of that material set drives this need to develop this core set of process modules to allow this intimate integration of these diverse subcomponents. So I'll talk a little bit more about that on the upcoming slide. But really a lot of focus on creating this a manageable set of process modules that can handle and manage the significant diversity of the types of materials that we want to integrate for these advanced systems. And then over on the far right, there's another piece of this, which is really essential, which is if we want to develop these high performance 3D-HI microsystems, you can no longer try to optimize the design in just a specific domain. So, my background is integrated circuit design. That's how I started my technical career. And I used to spend tremendous effort in focusing on the electrical performance of the design, and then asked for my partners to help me figure out the thermal and packaging solutions a lot of times after the fact, after most of the electrical design work was done. But this is a bit of a new paradigm where we really need to be doing co-simulation and co-verification of these 3D microsystems across mechanical, thermal, and electrical constraints, all at once. Because really just at the center of that Venn diagram, if you can really meet the performance requirements or the system requirements in all three of those domains, can you really deliver ultimately a reliable microsystem? Now, I would assert that this has been a challenge for a very long time in this area, but again, the 3D stacking of these different technologies provide additional challenges for how to manage thermal and or mechanical constraints, for instance, particularly in operation, but even in quiescent conditions and or even in fabrication, as we're trying to build the devices in the foundry. It can drive temperature profile requirements for the assembly and integration, which are challenging and unique. So the diversity of the materials that support these really advanced systems really are going to drive this innovation in a couple of key places to enable the success of our NGMM program. If you jump to the next slide, please. This is my best effort to really summarize on a single slide where we're headed and what our vision is for NGMM. I've got a couple of additional slides after this where I'll provide some supplemental information, and I'll dig into this a little further to give you a little bit more in-depth perspective. But at a very high level, this is kind of a summary of where we're headed with NGMM. The Texas Institute for Electronics, or TI, they are in Austin, Texas, were selected to implement NGMM and bring this vision to reality. And there in the image in the center of the slide, you're looking at the Montopolis facility, the Montopolis fabrication facility, which is in the southern part of Austin, out near the airport. This was actually the original Semitech facility that was built in the late 1980s there in Austin. And it's getting a new life and a new mission to support this NGMM program. And we've been very, very busy refurbishing and remodeling the facility to get it ready for this new mission. And Ty has had a very, very busy first year of this program in preparing this facility to take on this new role. On the left-hand side, you can see the intent to have this be a foundry base or a foundry services based model that's open to a very, very wide or large user base that includes private industry, partnerships with academia, and ultimately government applications, as I mentioned, for the broad national security missions. And then across the top, you can see sort of a span of technology readiness levels, or TRL for those that are familiar with the TRL terminology, really spanning all the way from fundamental research around 3D heterogeneous integration in looking at new equipment, developing new equipment that can support new and innovative approaches for 3D HI, as well as new integration technologies to integrate these devices together, and in particular, deal with, as I mentioned, the significant diversity of these materials on the prior slide. Also intend to support prototyping, quick-turn prototyping for research activities as well. But also uniquely are focused on maturing the process modules and the integration technologies to support low volume pilot production for defense applications and national security applications. And then along the bottom there is really the foundation of all of this. So in the banner, you can see really important for us is to develop this self-sustaining national capability for 3D HI research and development and manufacturing. And that self-sustaining piece is very important. We intend for this to be an enduring capability that will be around long-term. And so we're very, very focused on the sustainability model, the cost structure, and the investments that we're making now to establish this capability to make sure that it is financially sustainable long-term for user access long-term. The foundation of all of this is really this core set of integration processes I mentioned on the prior slide, where we need to effectively manage this diversity of materials for this integration. We have to do so very thoughtfully with a core set of process modules where, as I mentioned, we want to consolidate much of this capability into this one facility to help address the challenge of sending hardware across the country for different processing at different facilities. But at the same time, we don't intend to reinvent the wheel in every case. And so there are certainly partnerships that we're looking at for mature capabilities where it makes sense to do so. But the development of those integration processes is key. And then, as importantly, the 3D HI assembly design kit, or the design rules, or the design information that users need to successfully design systems in this infrastructure, in the new NGMM infrastructure, is critically important. And so partnering with the EDA companies and working with them to develop these assembly design kits that will allow users to design next generation systems in the facility is a critical part of the program. Next slide, please. So I'll just take a minute more to talk about TIE, who was selected for NGMM. They received our award from DARPA, along with a significant resource cost share from the state of Texas, to establish the TIE NGMM Center, or TNC. Always my favorite. Nested embedded acronyms are always my favorite. So this is a good example of that. But it really includes a significant investment in workforce development. There's really a large team that TIE has partnered with of leading defense and commercial companies, as well as small businesses and academia, to establish and stand up the NGMM capability in Austin. And I talked a lot about the Montopolis facility, or gave you some perspective of the Montopolis facility, which is in the lower right corner here. It's about a 65,000 square foot clean room space that will take on this new mission, as I mentioned, down near the airport. There's also a facility in the northern part of Austin on the University of Texas Research Campus, the J.J. Pickle Research Facility. This is currently, will eventually be about a 20,000 square foot space. We're currently in the process, TIE is currently in the process of retrofitting some existing space to expand the clean room space that's there, and build out a larger clean room to support research activities at this facility. If you jump to the next slide, please. So we recognized a lot of really critical folks helped establish this vision for where we're headed with NGMM. Carl McCants, who was at DARPA for many years, was just instrumental in developing this vision for how to lay out a facility and capability like NGMM. And others like Dev Palmer also had a significant involvement and impact in the program. And there was some recognition up front that, again, 3D HI is a very complex challenge. And I sometimes joke around a little bit that it seems like sometimes a bit of an infinite solution space, because there are so many permutations or different approaches that you can take to support 3D HI systems. So there was some recognition of that, and some work done in a phase 0 program or piece of NGMM that happened in 2023, 2024. And it was really an opportunity to engage the community broadly and understand what are the kinds of systems or the key systems that could uniquely leverage a capability like NGMM, and what are some of the important capabilities and technologies that we could target as we stand up this new capability. And so there were a couple of exemplars that were selected that are relevant to DoD applications, and those include an RF phased array radar, a focal plane array imager, and a compact power converter. And really, those 3 exemplars help define the initial set of EDA and the initial set of process modules and our initial requirements for our assembly design kit to help us establish and build out this capability with some initial constraints in a way to bound the problem so that we could be successful in standing up and maturing this capability. These exemplars defined, specific configuration of materials and integrated tiers and specific integration technologies that we were going to develop. And they also helped us to establish this initial set of integration modules to manage and deal with, again, the diversity of chips and materials. The goal is to really establish this initial process capability to support a wide variety of customer 3D HI microsystems. Next slide, please.
Apologies, everyone. It looks like we may have just lost Mike, but we will be returning in just a bit. Sometimes these things happen, technology issues, but please stand by as we wait for Mike to return and connect. In the meantime, if you have any questions, please feel free to send them into the live chat or the comment section. We'll be monitoring them. We are saving the questions until the end of the presentation after Mike's final slide, but please do send them in. And while we are still waiting for Mike to connect, if you want to learn more about the NGMM program, you can through the link that we provided on the screen. And in the meantime, folks, we'll be right back with a short commercial break.
AI is changing our world at a tremendous pace. We need to be prepared for these changes. We need to understand how AI is affecting our lives, our societies, and even our psychology. I believe that this is the most important work in the world right now. IEEE is bringing people together from all around the world to work on some of the world's most difficult problems. IEEE is my competitive edge.
In my research, we are developing social media analytics algorithms. Using our technology, we can make our society better. Thanks to IEEE, I have a good network all over the world, and I became a global leader. I believe IEEE will give many opportunities for your career development. IEEE is my competitive edge.
There's cybersecurity issues, there's aging infrastructure issues, there's climate change issues that need to be solved, and I'm really excited that in my career I get to work on those types of problems. As a young professional, IEEE has given me access to opportunities to go to conferences, meet really cool people in the field, and so I think what IEEE provides is access to the larger community, and I don't know where else you would get that. IEEE is my competitive edge.
Hey, Jonathan, can you please confirm audio for me?
Hello, everyone. Thanks for your patience. We do have Mike back on with us. It looks like he's still connecting, but again, this kind of stuff happens. So thank you for your patience, and we'll be resuming our presentation shortly.
Hey, Jonathan, can you give me an audio check? Hey, Jonathan, can you give me an audio check, please? All right, excellent. So if you can please jump to the next slide. All right, so that core set of exemplars really helped us establish this initial technology roadmap or process capability roadmap that you're seeing here. And on the left-hand side, what you see is a high-level summary of the initial process modules and capability that we're standing up, built around those exemplars. You can see up in the very top block the initial set of materials we're working with, spanning from silicon to indium phosphide to silicon carbide to mercad telluride. And you can see the planned capabilities lower left for bonding, where we're focused on both thermocompression and hybrid bonding for both die-to-wafer and wafer-to-wafer bonding. Through substrate via processes in multiple materials to support the integration of these diverse materials. And really a core set of enabling capabilities focused on copper routing for both damascene damascene dense interconnect, as well as lower density interconnect through RDL and bump. And then to help manage the diversity of the materials, some focus on reconstitution of sub 200 millimeter wafer sizes to support integration with 200 millimeter and 300 millimeter wafers. All of this is really foundationally supported by tool and process R&D. TIE has some history in equipment research, and that will continue in supporting NGMM and enabling the integration of these diverse technologies. And then ultimately establishing the 3D assembly design kit, as I mentioned, which is essential for the integration of these advanced systems and these advanced devices. I think I've covered most of what's on the right-hand side by kind of talking through the table on the left, with just maybe the caveat to mention that we have some focus in establishing security protocols to put in place to support ITAR and EAR compliant operations. And as I mentioned earlier, looking at some strategic partnerships where it makes sense in the implementation of NGMM. If you jump to the next slide, please. Now a little bit about the program plan and really where we are. We are about a year in. We just crossed over our year anniversary on July 11th. So we're about a year in to the first 2.5 years in phase one. Phase one is shown here, where the overall goal of phase one is to establish our baseline process technologies and capabilities. This is really focused on preparation of the materials, of the facilities, and readiness to install all of the equipment. And so there's some focus on refurbishment of the existing facilities and really procuring and installing all of the equipment that will stand up these processes. In parallel with all of that, we're working on initial process capability development and starting to work on the development of the required EDA infrastructure to support design of these systems. So it's been a very, very busy first year for the team at TIE and their partners, implementing really refurbishment and remodel of all of these two facilities, installation of the critical equipment, and then in parallel doing process development. At the bottom there you see there's an arrow looking or identifying a design challenge solicitation. So we have DARPA has an active RFI currently for NGMM. That RFI is up on the web at sam.gov, and we're asking for folks' feedback at this point for the ideas that they have for how they could utilize a facility like NGMM. And so at this point, it's just a request for information, but we provided some information about the technology roadmap, and we're very interested in the ideas that folks would have to utilize NGMM for new microsystem concepts. And so we're starting to just frame out what a solicitation might look like in the future for those kinds of ideas. At the end of phase one, the goal is to have an initial process capabilities established and an alpha version of the assembly design kit that can support the design of these 3D microsystems. If you hit the next slide, please. Phase two then is another 2.5 year cycle where we're really focused on now qualifying and operationalizing the capability. We are going to be doing 3D HI prototyping, building an instantiation of those exemplars that I showed you earlier, which establish and mature the process capabilities at NGMM. And also a focus on process improvement, automation of fabrication processes and assembly, automation of test processes, and some capability for digital twin as well. And so during this second 30-month cycle, we plan to concurrently run a design challenge, what we're calling an NGMM design challenge, where we're interested for those who are excited about early engagement with NGMM and have interesting ideas for microsystems that we could build. We want to fund some performers to partner with TIE and also build some additional Exemplar Microsystems during phase 2, in addition to those 3 that I showed you previously. And so if you hit the next slide, the last one here in this buildup is really just to show that our end goal is really to enable, as I mentioned, broad spectrum from research through prototyping through pilot production, with a foundry services model that's open to a large community who are interested in building these kinds of systems, and doing it in a way that is cost effective and self-sustaining long term. If you jump to the next slide, please. Recent accomplishments for us to give you a feeling of where we're at, and I'm looking forward to making a couple updates to this. We've been making tons of progress over the last few months. We have doubled the clean room space at the research facility that I showed you on the previous chart. So that first phase of clean room expansion has opened. All of the die to wafer hybrid bonding equipment has been installed. You can see it in sort of a pinwheel diagram on the right-hand side here. And our first silicon die to wafer bonding was completed in May. The very first die to wafer. There was some mechanical work that was done initially focused on alignment and overlay experiments. And we now have moved on to some electrical interconnect, some electrical bonding, where we're starting to test electrical test structures. And so the process development is moving forward as we continue to work to complete the refurbishment activities and the installation of the equipment at the 2 facilities. In the refurbishment space, there's been completion of some major upgrades to some critical infrastructure that supports really both fabs, but ultimately supports the Montopolis facility in this case, some of the critical infrastructure that's there for all the fab operations. And then TIE continues to hire key leadership in critical areas for the development of this technology. So it's been a very busy first year with lots of activities happening in parallel, and I'm pretty excited as we start to move into year 2 here to continue to support the process development for these technologies. If you go to the next slide, please. Here's a quick look at the NGMM Design Challenge program that I mentioned previously, really as an opportunity for early engagement with NGMM. Again, we're just starting to frame this out, and we've got this RFI that's open through the 29th of August to get some ideas from the community. But the goal is ultimately to support long-term sustainability and the technical roadmap for the NGMM Center. And notionally, you can kind of see what we think this looks like here in the block diagram with a program structure where the design of the test structures and the building blocks for the microsystems using the release of the assembly design kit will be done by a partner with TIE. And then ultimately that partner will be responsible for seeking procurement and fabrication of the individual building block components. And then ultimately partnering with TIE to do the 3D heterogeneous integration of those components, likely some split of the test and reliability analysis of those devices between TIE, who has some capability in-house, and their partner who's building or designing the system. And then we're looking for an opportunity, of course, to leverage the learning to upgrade our models and the 3D assembly design kit as part of that as well. Next slide, please. So here's a quick look at, we're quite excited. I'm quite excited. It's getting close. So we're very busy getting ready for our inaugural summit, our summit event, which will be in Austin, Texas on the 27th and 28th of October. We're going to host an event there, inviting a broad group of stakeholders from the community. If you're interested, please jump on, and our website is up and live and registration is open now. And we really want to engage the community broadly and give an opportunity to kind of see inside NGMM, talk with the TIE team directly about early engagement, learn more about our program timeline and other ways to get involved as we move forward in establishing this vision for NGMM, talk more deeply about our technology roadmap and provide a little bit more insight into the development there and the capabilities that will be there. And then also just give a little more in-depth picture of what we're up to in establishing and installing the infrastructure and equipment, and kind of our key milestones as we push forward with process development. So I hope you'll consider taking a look. We're in the process of updating the agenda that's on the site as we continue to refine that and get it fully fleshed out. But be a really good opportunity to learn more about what we're up to with NGMM and have an opportunity to engage directly with the team who's standing up the capability. And I think maybe the next slide is my last slide, is just to say thank you very much and provide an opportunity for you to reach out to DARPA if you're interested either in NGMM, or you're interested in other ongoing programs or opportunities at DARPA, or you're interested in coming to DARPA to work. I would encourage you to reach out and connect through DARPA Connect. and engaging with the team there. And so thank you again, IEEE, very much for hosting me today. My sincere apologies for the technical interruption in the middle. I apologize for that. I'm really glad that I was able to jump back on and somewhat seamlessly finish. I appreciate it. And thanks for Jonathan for helping me out there a little bit. And with that, I think we have a little time for questions if there are some.
Fantastic. Thank you so much, Mike. And no worries. You know, again, as someone who works in with technology very closely, I'm sure you understand that there's these things kind of happen all the time. So no worries at all. We're just glad to have you back. So Mike, so folks, we are now at the Q&A portion of the webinar. Please send your questions in the comment or live chat section, and we'll load them on the stream for Mike to answer. Mike, we do have a couple questions from our audience members.
Great.
The first question was from our audience member. Let me just pull it up real quick. Anderson. So Anderson asked, is a disruptive mathematical framework for automation and optimization of the 3D HI complex processes in the scope of NGMM, or is the focus on the materials for 3D HI?
Boy, I probably need to learn a little bit more about that. I would say that 3D HI and the integration of these materials, as I mentioned before, is certainly a very complex technology and process to establish. And I think we are interested in learning from the community about what innovative ideas they have in helping us with that endeavor. I say that there certainly could be an opportunity for alignment with NGMM, but interestingly, I'm wondering whether there's perhaps some interest more broadly for our Microsystems Technology Office, MTO, at DARPA that might align there.
Thanks, Mike. And thank you, Anderson, for the great question. This next question from our audience member, Tim. Tim asks, will there be training of AIs to help designers in their process development?
Wonderful question, Tim. There's a lot of work going on in this space now. I think to help in ways that we might be able to leverage AI in EDA tools, in architectural assessments and studies, and helping us understand the highest performance or most optimal way to integrate these materials together into these advanced stacks. And so I'm aware of some work that's going on in this space with an intent to help us really optimize these designs and also increase the chance of first pass success in building these complex devices. So I'm aware of some activity that's going on in this space broadly in the community. We don't have a core focus on that for NGMM, but I know that there's a lot of activity in that area.
Fantastic. Thank you. And thank you, Tim, for the great question. So while we're waiting on some more audience member questions, I'd like to ask you some questions of my own. So the first question, so what kind of partnerships or proposals are you most interested in from the research community?
Yeah, great question. I think that really partners and stakeholders from all across the community, in all the way from academia through commercial or dual use applications are very, very interesting to us. And we really are interested in the very broad diversity of ideas that folks have since we're very focused on establishing this flexible capability, right? We selected these couple of exemplars to help us frame the problem. But the intent is to support a much broader application space and a much broader mission set than that. And so we believe that with this core set of process capabilities that we're standing up, that folks can really innovate and come up with lots of new ideas for how they could leverage that to build new and diverse systems. And so we're really interested in hearing from them their ideas and how they would leverage this capability to go after lots of different challenging problems. And I think it would span all the way from academia to small business to private industry to certainly the defense and national security community.
Fantastic, thank you. So we do have another audience member question. Audience member Krishna asks, you did not mention integration of photonics. Any comments?
Yeah, thanks, Krishna. Again, I appreciate that tee up too. Right now, in this immediate term, photonics is not in scope for NGMM. We're not planning on standing up photonics capability right now. However, the reason I'm so thankful that you asked is I showed that initial technology roadmap or capability roadmap there in what we're standing up. And again, given the diversity of 3D HI and the complexity of 3D HI, the exemplars we selected provided an initial sort of constrained problem for us to go after, or a constrained challenge for us to go after to establish this capability. But we do want to be talking to the community about what their needs are. In fact, in the RFI, one of the things we asked was for some feedback about potential gaps in our technology roadmap, where, you know, if we supported a particular process module or a particular a solution, that it might open up this broad application space. And so we don't intend for that technology roadmap to be frozen as it's shown, but instead expect that will evolve over time. And we're interested in hearing from folks their ideas or perspectives on the kinds of things that we should be considering adding.
Fantastic, thank you. And thank you, Christian, for the question. This next question, how many of the prototypes are planned for deep space application?
Yeah, good question. We certainly have the focal plane technologies, which may align with remote sensing or space-based applications. And so I think in the current exemplar set that we have, that might be the most relevant, although the compact power converter as kind of a point of load power solution has very broad application. And certainly there are opportunities to implement rad hard point of load power, compact power converters that can support space-based applications. So I think we have some overlap fairly immediately in our exemplar applications, but certainly we're open to ideas from others in the community through our design challenge for potential space-based applications that would be interesting.
Thanks for the question. This next question from our audience member, Blake. Blake asks, can you say what security clearance is required to participate in NGMM?
Yeah, great. Sure. The NGMM, again, is in its inception is meant to be an open facility, a fabrication facility, right? A foundry-based service. And so the intent is that NGMM will be supporting commercial applications or dual-use applications in addition to the national security or defense-based applications. And so really security clearance is not required to participate and or to partner with TIE to develop these kinds of systems.
Fantastic, thank you. David asks, how does this interact with GCPU?
I might need help with that. I'm not sure I know the GCPU acronym immediately.
And with that being said, David, if you'd like to elaborate on what GCPU is, please just feel free to send another comment in the live chat, and we'll be happy to address your question. So I think that's it for audience member questions so far. While we still wait on David's elaboration, let's go to some more back to some of the other questions that I had. So Mike, apologies, let me also remove that off screen. So Mike, DARPA has a long history of leading breakthrough innovations from stealth tech to the internet or to you name it. NGMM seems to be another bold step in that direction. So my question is, can you share what inspired the launch of the NGMM program? What specific challenges is it trying to solve, and how does it build on DARPA's previous efforts?
Yeah, great. Very happy to answer that question. I spoke to that a little bit in my presentation, and trying to kind of tie it back to really this sustained investment that DARPA has made, or that the Microsystems Technology Office has made in the establishment of some of the building block components and really the foundational research in 3D HI to establish this capability. And there's some recognition that the consolidation of this capability with some flexibility enabled by this fairly diverse set of process capabilities really can drive innovation to solve new challenges for the warfighter. So and dual use in commercial applications. And so I acknowledge that the construct for this program is a little bit different than some other DARPA programs, right? We're focused here. It's not unprecedented. There have been prior activities where DARPA has made investments in establishing capabilities and developing infrastructure. But this is a little bit different. But the intent here is really to establish this foundational and enduring capability that really can be leveraged to make significant performance improvements on a huge number of systems, both for national security as well as commercial applications.
Fantastic, thank you. And so it looks like we did get clarification from
Oh,
David.
great.
So in regards to GCPU, he's asking about graphics and CPU. So I
Ah,
guess in that context, how does this interact with the graphics CPU?
wonderful. Thank you. I appreciate it, David. I am part of the fun at being at DARPA is an endless set of acronyms, and some of them I know instantaneously. Others it takes me a minute to
There's a
calibrate. So
lot of
thank you.
acronyms.
Yeah, there's so many and very helpful. Thanks, and happy to answer this. So certainly there are applications for high performance compute. For graphics, CPU, for accelerators, and the kinds of things that we might be thinking about there are things that would enable new and novel memory technologies for ultra high bandwidth interconnect between compute and memory. Techniques that might help us both with energy efficiency and or managing the thermal challenges associated with the integration of high performance compute in different platforms. The 3D stacking, as I mentioned, sort of has its challenges associated with thermal. We have a core piece of the research for NGMM that's focused on helping to address that problem. But certainly the ability to integrate these stacks and integrate technologies like gallium nitride and diamond and others that can help us with some of the thermal and power challenges can be very advantageous. And then one of our exemplars, the point of load power converter or compact power converter, also is interesting in this application space where you can really do right at the point of load down conversion or power conversion there that can be reactive and responsive to compute, and therefore can be very efficient there right at the point of load. So some overlap certainly in what we're doing, and a lot of opportunity to look at new concepts for high performance compute.
Fantastic, thank you, and thank you for the clarification, David, and for the great question. So I think we're going to close it off after the last last few questions. So the first question, our audience member Tina asks, are power electronics considered to be part of NGMM 3DHI? If yes, what about WBG?
Yeah, thank you. The WBG one I do know, wide bandgap or ultra wide bandgap, and so certainly, Tina, yes, that is absolutely true. And part of our compact power converter work is in this space and working in this space. And we certainly wide bandgap and ultra wide bandgap are in scope for us in the types of materials or types of devices that you would leverage to build these kinds of systems.
Fantastic, thank you, and thank you, Tina, for the great question. So, actually, unfortunately, folks, we are running out of time, so we're going to close it off with this one last question.
Great.
So, Mike, what can attendees expect from the upcoming NGMM Summit in October, and how can they get involved?
Yeah, great. Looking forward to having an opportunity to engage with the community. MTO just hosted our open house event or our Spark Tank event in Denver in July. And I presented about NGMM at that open house and then had an opportunity to engage with the community there about their innovative ideas for how to utilize a capability like NGMM. And it was so much fun. And there were so many exciting ideas for how to utilize this capability moving forward. And so I'm really looking forward to hosting this event, this summit, which is really focused on NGMM and provides this opportunity for direct dialogue with the DARPA NGMM team, the Thai NGMM team, and really just a time to focus for kind of a day and a half on where we are with NGMM, the progress that we're making, and opportunities to engage early in activities like the design challenge and other opportunities to partner with Thai. So just really excited to bring the community together, have an opportunity to share with them the latest and greatest of where we are and where we're headed, and then have an opportunity to interact with them with some fairly significant opportunity for social interaction to get some feedback and get their ideas.
Fantastic, thank you so much. So, all right, everyone, that is all the time that we have for today. I know we didn't get to everyone's questions, and I know we do still have questions coming in. If you do, if you would like us to answer, excuse me, if you would like to ask us those questions, feel free to send those over to us. You can either do so to IEEE-USA, or you can reach out to Mike directly if you like, and reach out to DARPA as well. Mike, thank you so much for joining us today and for sharing your insights into DARPA's current initiatives, especially the exciting work being done through the NGMM program. It was a pleasure having you with us today.
Likewise, thank you, and apologies for the somewhat embarrassing interruption in the middle, but I really appreciate your help in doing that. And yes, I tried to make certain today I would have all the right technology luck on my side to have this go seamlessly, but alas, I was not able to do so. But thank you for your help. Appreciate the opportunity.
No worries at all. It was a great presentation, regardless. And thank you to our audience for tuning in and for your great questions as well. And to our partners for today's webinar at DARPA for connecting with us and setting this up. A few announcements before we close things off today. First, there's less than a month left to submit your nominations for the 2025 IEEE-USA Awards. Each year, these prestigious awards honor excellence in professionalism, technical achievement, and literary contributions that elevate public understanding of the engineering profession in the United States. If you know someone who deserves recognition, now is the time to act. Nominate a deserving individual before the deadline slips by. Full details on award categories, eligibility, and the nomination process are available on our website. Next up, IEEE-USA is still accepting nominations for its 2027 Board of Directors. This is your opportunity to help shape the future of IEEE-USA and make a lasting impact on the engineering profession. We invite dedicated members to step forward or nominate qualified candidates for leadership roles. The nomination deadline is September 10th. Finally, we're thrilled to welcome Philip Smith from DARPA's Tactical Technology Office to the upcoming IEEE-USA iWork AI and Autonomy Summit in Grand Forks, North Dakota on September 10th. Don't miss this opportunity to learn directly from one of the leading minds in defense innovation. iWork is exactly 3 weeks away, so make sure to secure your spot now and be a part of the conversation that's driving real change. If you enjoyed the content presented in today's webinar, be sure to check out our extensive catalog of other presentations and publications available on demand on our website for your viewing pleasure. And if you haven't yet, please be sure to like and subscribe to our IEEE-USA social media channels. And don't forget to check back daily for updates on upcoming events. Have a great day, everyone.
Hi, I'm Mark Askelson, Associate Vice President for Research with a focus on national security from the University of North Dakota. IEEE-USA iWork Summit is where aerospace, space, and defense collide with cutting-edge tech. If you are a leader in industry, academia, or government, this summit is for you. You'll hear from DoD, Northrop Grumman, and AFRL Regional Network Midwest, and connect with the people shaping what's next. And I will see you on September 10th at UND.